So FastSpeech is a network proposed by Microsoft, which tried to avoid or overcome the limitations of Tacotron 2. So because the speech output is non-robust, because the alignments generally these are not hard alignments, whatever alignments are learned by this attention module, these are soft alignments. So instead of that, in FastSpeech, you provide hard alignments between phonemes and MEL spectrogram using a duration predictor. And to overcome the problem of slow inference speed, you can use a feed-forward transformer. I'll go into these details in the next few slides. And you can also adjust the voice speed. Since you have control over the duration, you can also increase or shorten the phoneme duration and hence control the speed at output. And you can also give, you can also include pauses in between the phonemes. So for improving the prosody. So these are the main features of FastSpeech. So this is the basic architecture of FastSpeech. It is dependent on feed-forward transformer networks. You would have already seen transformer in the previous slides. And we have, this is the input side, the phoneme side, this is the output, that is the MEL spectrogram side. At the input side, there are n such blocks of feed-forward transformer, and similarly in the output side also you have n such blocks, and you have a length regulator. So basically what happens is phonemes are smaller. Again, you need to decompress it to get the MEL spectrogram frames. So the length regulator essentially expands the phoneme sequence to match the number of MEL spectrogram frames. So this is the internal architecture of the feed-forward transformer. So transformer uses self-attention and it has a multi-head attention to extract cross-position information. And in the traditional transformer used, we have dense convolution networks here. Instead of that, in this particular network, in FastSpeech, we have 1D convolution layers. So transformer networks was inspired from machine translation, wherein the word ordering used to change during translation. Suppose we have English, I am going home, and in Hindi it will be main ghar ja raha hoon. Home is at the end in English, but ghar, which is its translation, appears towards the beginning in Hindi. So the word ordering changes, because of which you need a dense network in the basic transformer module for the purpose of translation. But in here, the adjacent hidden states are more closely related. Because of this, we can do away with the dense network and just use simple 1D convolution layers. And there is an add and normalization layer that is used in the conventional transformer too. We also want to expand the phoneme sequence to match the length of the MEL spectrogram sequence. I'll show you with an example. So this is our hidden states at the phoneme sequence level. So the function of a length regulator is to match the length of the phoneme sequence to the length of the MEL spectrogram frames. Essentially, the hidden states corresponding to the phoneme sequence, they are repeated to match the length of the hidden states of the MEL spectrograms. So what happens here is that we pass this through a duration predictor, which will be explained in the next few slides. And we get this, and then this says that the first phoneme, that is this red one, has to be repeated 2 times. So we have 2 frames here. Then this green one has to be repeated twice. We have 2 times here. This is what the duration prediction gives us. And this the blue hidden state has to be repeated thrice. And the yellow one just once. So these are all hidden states corresponding to each phoneme essentially, and they are expanded to match the length of the hidden states of the MEL spectrogram. And this alpha parameter is a parameter to control the speed. So if I have alpha greater than 1, I can slow down the speed. If I have alpha less than 1, I can increase the speed of synthesis. So as I mentioned earlier, the hidden states corresponding to the MEL spectrogram is a function of the length regulator, which takes input the hidden states corresponding to the phoneme sequence, the output of the duration predictor, which is D, and this alpha parameter. Okay, so yeah, so these are just mathematical details. So you have H phoneme, that is hidden states of phoneme, going from H1 to Hn, where n is the length of the input sequence. And you have the duration prediction has to give this vector d, going from d1, d2 to dn, where d1 corresponds to the number of frames corresponding to H1, the hidden state of the phoneme sequence, the first phoneme, and dn corresponds to the number of frames for the last phoneme in the text. Okay. And again, alpha is a hyperparameter for speed control. So, as I mentioned earlier, if I want fast to speed up the synthesis output, here I have alpha equal to 0.5. Then I just multiply this 0.5 with this. So, I get 1.5 and 0.5, just this. But I cannot have number of frames in decimal values. It should be integer values. So then we just round off, or here we use a ceil operation. So we have 1, 1, 2, 1. So if the output of this particular thing is 1, 1, 2, 1, then the synthesized output is speeded up. So next, how do we produce or how do we predict the duration corresponding to each phoneme in the text? During training in FastSpeech, the duration predictions are obtained from a teacher model. The teacher model used is an autoregressive TTS. It could be the Tachytron 2 or some other autoregressive TTS like transformer. So you already have a trained system. You pass the entire training text through it or training data through it, and you get this alignments predicted by the autoregressive TTS. That is, these are basically the attention alignments for all the training data, and this is what we have during training. And for prediction during synthesis, we have to learn this small duration prediction network. So the duration prediction network consists of 2 layers of 1D convolution networks with normalization, and you have a linear layer at the output which gives a scalar value which corresponds to the phoneme duration. So this duration prediction is only done during, it is learned during training, but it is not used during training. It is only used during synthesis. During training, the duration information is obtained from the attention alignments from the autoregressive network. And another thing about FastSpeech is that instead of using the actual speech waveform, or instead of actually using the MEL spectrogram extracted from the actual audio waveform as the output, we use the MEL spectrograms generated from the teacher model. So, the FastSpeech model is trained with training text and the MEL spectrograms generated by the teacher network. Again, this is a disadvantage, and that's why we have another system called FastSpeech 2, which uses the ground truth MEL spectrograms rather than using the MEL spectrograms generated by a teacher model. So let's take the same example wherein Tachytron 2 made mistakes during synthesis and how it is corrected in FastSpeech. So this is the FastSpeech output.
To deliver interfaces that are significantly better suited to create and process RFC 821, RFC 822, RFC 977, and MIME content.
So you could see there was no repetition at 70, and then the content word was spoken correctly without skipping. But the disadvantage of FastSpeech is that it has this complicated training of two model, like this teacher-student model. You have this autoregressive network feeding to a non-autoregressive FastSpeech model. And since we are using, as I mentioned earlier, the MEL spectrograms predicted by the teacher, that also becomes a problem because there is information loss already. And the duration information, that is this part, is extracted from the teacher model. It may not be correct. So how do we solve this problem? That is what FastSpeech 2 does. Instead of using the target MEL spectrograms generated by the teacher model, we use the ground truth MEL spectrograms. And the duration information is obtained from an external alignment. So you get rid of this teacher model but of course there's the downside that you have to use an external alignment for this. And in addition to duration information, pitch and energy information are also included for producing more variation in the synthesized speech. So this is an architecture of FastSpeech 2. It is similar to FastSpeech, except that here in the output you have the ground truth Mel spectrogram, and the variance adapter contains energy and pitch information too, pitch prediction and energy prediction. So yeah, here you have the duration prediction, length regulator. It produces the same number of frames as that in the Mel spectrograms, and then you extract pitch from it, you extract energy from it during training, and then these energy predictor, pitch predictor, duration predictors are learned. You can include any other predictor if you wish. And then during training, from the ground truth we extract pitch and energy values, but during synthesis, whatever has been learned, those energy and pitch values will be used. So yeah, and for getting this duration prediction, for the training data, an external aligner like Montreal forced aligner or HMM based aligner can be used, and the ground truth values of energy are used during training, and synthesis everything is predicted. So here is an example comparing FastSpeech and FastSpeech 2.
And were occupied as a rule by 10 to 15 people when the prison was not crowded, but double the number was occasionally placed in them.
And the same text synthesized using FastSpeech 2.
And were occupied as a rule by 10 to 15 people when the prison was not crowded, but double the number was occasionally placed in them.
So you can see, because of this energy and pitch information being included, and the prosody is better in FastSpeech 2 compared to FastSpeech. So now in all the architectures that we have seen, that is Tachytron 2, FastSpeech and FastSpeech 2, Mel spectrograms are produced. So then again we need to make use of a vocoder for speech synthesis. So WaveNet is one of the vocoders. We have WaveGlow and we have mini GAN based vocoders. I have referenced them towards the end of this talk. So we have parallel wave GAN, Mel GAN, high fidelity GAN, style Mel GAN, and so on. So these are all like various vocoders that are available online, and you can choose whichever vocoder you want. Now the next stage is that instead of giving text to this end-to-end system to produce this intermediate Mel spectrograms and then passing it to a vocoder for generating the audio wave file, can I do it in one shot? So that's a question. Can we get rid of this intermediate Mel spectrogram representation? So now even the definition of end-to-end TTS has changed. Now it's you give the waveform, you get the you give the text, you get the waveforms directly without going through this intermediate Mel spectrogram representation. And when you just consider the Mel spectrogram representation, there is some information loss, because you take the spectrogram which is already the absolute value and then you get it in the Mel basis, but then even when you take the absolute value to get the linear spectrogram, you lose out the phase information, and so the information gap between the text and Mel spectrogram is much larger compared to that between text and waveform, the actual audio waveform. And now there are many such completely end-to-end systems such as FastSpeech 2S, WITS, which is conditional variational autoencoder with adversarial learning, or JETS, which is jointly training FastSpeech 2 and Hi-Fi GAN. Okay, so there are a lot of advancements currently in the past 1.5 years where they have shifted to generating audio samples directly by getting rid of this Mel spectrograms. And along with conditioning on text, you can also condition on the speaker language in case you're doing multi-speaker training. In case you have multiple speakers in your database, you can also include speaker embedding in case you want to do multiple languages. You want to train a single model for multiple languages. You can use language embedding, or you can use various style token embeddings also. So these all can be included during training. So coming to the pros and cons of end-to-end TTS, the advantages are it produces really good speech, high quality speech, and they are easy to train. But the disadvantages that to produce this good quality speech, it requires a lot of training data, at least from the typically used is 25-30 hours of data. And these are computationally intense. All of them require GPUs for training. Now, another important question is how do we evaluate these TTS systems? So, in ASR systems and all, you have this word error rate. You could compare it with the ground truth text and say, okay, this is where these words are, erroneous, and then I can calculate the word error rate. But how do we do that in TTS systems? So you have majorly two types of measures, objective and subjective. Objective measures are in comparison with the ground truth. So you have the ground truth wave file, and then for the same ground truth wave file, you have the text, you pass it to the system, you get the synthesized wave file, compare them. One of the measures is Mel-Kapstrel distortion scores. So you get the Mel spectrum across both of them, you align them, and then you can get the mean squared error. So this is the Mel-Kapstrel distortion scores or MCD scores. And then since TTS, the end consumers of TTS are people, we also have to do subjective evaluation wherein people listen to your system and give a rating. So we have mean opinion scores. Suppose you are comparing different systems. You synthesize the audio wave file across all these systems, play them in random order to the listener, and ask them to listen, rate on a scale of 1 to 5, 1 being very poor quality and 5 being human-like quality. So, and then you average out and get this mean opinion score. And then in addition to doing this mean opinion score, in addition to asking listeners to listen to this synthesized examples alone, you can also include randomly a few natural utterances or a few ground truth utterances to see how their perception is. And then you, whatever mean opinion score that you get, you can now normalize it with respect to the score obtained for these ground truth examples. So that is nothing but degradation mean opinion score. And then you also have pairwise comparison tests where you ask people to listen, okay, is system A better, is system B better, and so on. So even in the TTS domain, even evaluation of TTS systems itself a big research area. And there are also other research areas. There are multilingual aspects such as how to do multilingual training, which are the best strategies to be applied, how do we handle bilingual, because all of us, when we speak like our own native tongue, we also tend to include words from English. So this is code mixing. So essentially Indians are bilingual speakers, at least bilingual speakers. So multilingual training, bilingual code mixing is again a big challenge. And how do we bring in prosody in speech? So depending on the domain, the way a news reader reads or the way a story has to be read out to children, the prosody varies across them. So how do we incorporate those aspects into a general domain TTS? So again, expressive voice, emotional TTS, these are all different research areas. And can we do voice conversion? That's also a very important area. Can we have the same text speaking in somebody else's voice by specifying a target voice? That is also a big research area. So another big area is how do we synthesize conversational speech? So in our training data, most of our training data has very well formed sentences. So how do we deal with conversational speech when sentences are not complete, or how do we include the appropriate prosody in that particular conversational speech? All these things are very important research areas. And in addition to all this, it's not just end to end is easy to train, so everybody is just doing end to end just because it produces good quality speech also. No, people are also looking at hybrid systems. Can we have hybrid unit selection based end to end? Can we combine the vocoder in HTS? Can we do so? Lot of research area and hybrid systems are also being carried out. These are some of the resources that are available online in case you're interested in building TTS systems or you want to have some hands-on training. You can have Festival. FestFox is essentially for USS systems. HTK, HTS, I have given the links. These are for HMM-based systems. Merlin Toolkit is for the conventional neural network-based TTS. We have ESP-NETs. It's Johns Hopkins University's toolkit. This has both ASR, TTS, speech enhancement and so on. And there are other online resources like we have NVIDIA Stackatron 2, Wave, Glow, Coder, which are online. And many of these, many of the things that we use are many of the toolkits that we use are mostly from open source toolkits. And for training TTS systems in Indian languages, we have developed an Indic TTS website. If you're interested, you can go and have a look at it. These are the additional references that have been used in this talk. These are the additional references that we have referred to in this talk. So if you have any questions on TTS, you can contact me during the TA Contact Us. Thank you.